In the last lecture, we learned the strengthening mechanisms. One of the strengthening mechanisms is string hardening or cold working, which is used a lot in industry to form material into desired shape. And here is the dislocation structure in titanium after cold working under microscopic examination. So you can see those dislocations. The dislocation density increases with deformation by formation of new dislocations. And as dislocation density increases, distance between the dislocations decreases, which means the dislocations are close to each other. And on average, the dislocation string interactions are repulsive. So because of that, the dislocation motion is hindered by presence of other dislocations. Therefore, the material will be strengthened. We know that after string hardening or cold working, the tensile strength and yield strength of the material will increase, while the ductility of the material will decrease. In addition, at microscopic level, the grain shapes will change as well. The grains are elongated. For example, the aluminum beverage cans are formed by deep drawing, which is a form of cold working or a cold working technique. So let's take a look at the shape of the grains before and after deep drawing. So before deep drawing, we have a piece of aluminum, and here is the photomicrograph, and from this micrograph we can see that the aluminum grains are equiaxed, which means they have approximately the same dimension in all directions. After deep drawing, we have this aluminum beverage can formed, and now the microstructure shows that the grains are elongated in the direction of stretching. And this is the simulation for deep drawing process. So why is heat treatment necessary after cold working? We already see that the microstructure of cold worked workpieces is strongly deformed by the high forming forces, and it reduces the ductility or deformability of the workpiece. So if the workpiece is to be further formed in this condition with lower ductility, which means brittle, then the risk of cracking increases. However, in fact, many workpieces and semi-finished products have to be formed several times in the course of their production in order to reach their final state. So, the aim of heat treatment must to restore the deformed crystals of a reshaped microstructure to their original shape. So here, in this case, the heat treatment after cold working, we have a term for it. It's called recrystalization annealing. But in general, we're going to learn many other types of heat treatment later. So in general, heat treatment defines processes that specifically change the properties of materials by means of controlled heating and cooling. This animation shows the change of the microstructure for a piece of metal, a rolled metal, before and after recrystalization annealing. So before the annealing, the microstructure or the grains are elongated in the direction of the rolling. After recrystalization, the deformed grains regain their original shape and the material regains its ductility. So the aim of heat treatment after cold working is to restore a deformed microstructure to improve its deformability or ductility. So heat treating cold worked metals brings changes in structure, mainly the microstructure, and in turn will affect the properties of the material. As a result, effects of cold work are reverted. So mainly for the mechanical properties of the material, for example, will revert back to pre-cold worked properties, and also physical properties such as electrical and thermal conductivities will recover to their pre-cold worked states. But again, the extent of the recovery depends on the extent of the annealing process. Okay, again, this type of heat treatment is termed as annealing. So annealing, as I said, is a heat treatment. So, for example, if we have a piece of iron or a piece of steel, then we want to do annealing. Usually we will have a furnace in the lab. So in the furnace, you have some knobs here. And annealing happens at an elevated temperature. This temperature is below the melting point. For example, let's say we bring the temperature to 200 degrees Celsius. So we bring this furnace to 200 degrees Celsius. At that temperature, we're going to put this piece of metal into the furnace and hold it for a certain period of time. For example, hold for 1 hour. And after this 1 hour, we're going to bring the sample out and put it onto the table. Let it cool down naturally to room temperature. So this is the annealing process. Happens at an elevated temperature, therefore it's called heat treatment. Here's one example or plot of the annealing process or after the annealing process for a certain material. I believe this is a brass alloy. After 1 hour of treatment at different anneal temperatures, and the result shows the tensile strength versus and ductility of the material. Tensile strength and ductility of the material at different annealing temperatures. So for example, at 200 degrees Celsius here, after we put the metal into the furnace for 1 hour, after annealing is done, the ductility increased from this point here to this point, and the tensile strength decreases. There are 3 annealing stages. The first stage is called recovery. Usually happens between 100 to 200 degrees Celsius. Second stage is recrystalization, is between 200 and 500 degrees Celsius. And the last stage is the GrainGrowth, which is usually above 500 degrees. The first stage is called recovery. During recovery, some of the stored internal strain energy is relieved by virtue of dislocation motion because of the elevated temperature, so atomic diffusion will be much easier to happen. So as a result, there is some reduction in the number of dislocations because of the annihilation of dislocation. So let's see how does the annihilation of dislocation happen. Scenario 1, we have 2 edge dislocations present here. One is on the top, one is on the bottom. They are actual half plane of atoms. So the other half is missing. That's why this is the edge dislocation or a dislocation. And this dislocation will create stress and strain in the surrounding area. So because of the elevated temperature, atoms will diffuse to the region of tension will go into those spaces. As a result, the half planes come together, or the actual atoms will fill into the gap, so there's no more actual half plane of atoms. So we have 3-4 rows of atom, so there's no distortion within the lattice structure or crystal structure. So this means dislocation disappeared, and we call this dislocation annihilation. Second scenario, so the reduction in the ductility is because the motion or the dislocation motion is impeded. So here's one example. If we have a dislocation in another orientation, this dislocation in red becomes the obstacle for the blue dislocation to move. Therefore, the material is more stronger or less ductile because the dislocation motion is blocked, cannot move to the right. Now, again, because of the elevated temperature, the atoms diffuse up by vacancy diffusion. So it looks like this dislocation now climb up to another plane or to another slip plane. So it can slip to the right without obstacles. So dislocations of the opposite sign will meet the other dislocation and annihilate. So again, both dislocation will disappear. In summary, during recovering, there is some reduction in the number of dislocations. Some of the internal strain energy is relieved, and physical properties such as electrical and thermal conductivities recover to their pre-cold worked states. Next stage, if we increase the temperature during the heat treatment, is called recrystallization. Is the formation of a new set of strain-free and equiacid grains. Again, that means the grain have approximately equal dimensions in all directions. And those new grains have low dislocation densities. They are small in size and also are characteristic of the pre-cold worked condition. And the driving force to produce this new grain structure is the difference in internal energy between the strained and unstrained material. So the new grains form as very small nuclei and grow until they completely consume the parent material, which is a process involving short-range diffusion. So here is the microstructure for the grain during the recrystallization. So this is the brass before heat treatment, after 33% of cold work. So you can see the grain size are big. And after 4 seconds of heat treatment at the given temperature, which is 580, we can see those recrystallized grains. Those grains are much smaller than the original grain size. And also, those grains are not just grow on the old grain, but actually it replaces the old grain. So it consumes the parent grain and becomes smaller grains. And after 8 seconds at this temperature, 580 degrees Celsius, all grains in cold worked materials have been consumed or replaced by finer grains. So during recrystallization, the mechanical properties are restored to their pre-cold worked values, which means the materials become more ductile and more softer but weaker. The recrystallization behavior of a particular metal alloy is sometimes specified in terms of the recrystallization temperature. It's the temperature at which recrystallization just reaches completion in 1 hour. Typically, it is between 1/3 and about 60% of the absolute melting temperature of a metal or alloy. For example, in this given alloy, I believe it's brass alloy, based on the annealing diagram, we can see the recrystallization begins here and complete at 500 degrees Celsius. So the recrystallization temperature is about 500 degrees Celsius. The value of the recrystallization temperature for a given metal or alloy also depends on several factors, including the amount of cold work and the purity of the metal. So the recrystallization temperature decreases with increasing cold work, and it decreases with increasing purity. And also, this recrystallization temperature is used to classify the plastic deformation operations. So for the deformation above this temperature is termed as hot working, and for the deformation below this temperature is termed as cold working. And after recrystallization, the next stage, or if the heat treatment continues, the next stage is grain growth. So it doesn't have to happen if you don't hold the specimen at the elevated temperature. But if we do, as it continues, the grain start to grow, becomes bigger. So it occurs by the migration of grain boundaries as heat treatment continues. And the average grain size increases during the grain growth. Small grains will shrink and ultimately disappear, and large grains continue to grow. It will consume the smaller grains. And as a result, you can see this is after 15 minutes at the same temperature after recrystallization complete. The grain are much larger or much bigger than the end of the recrystallization stage. We have been discussing grain sizes a lot, from the grain size reduction in strengthening mechanisms to the grain growth in heat treatment. The reason why we care about grain size is because it influences the material's properties. Metals having small grains, they are relatively strong and tough at low temperatures, whereas metals having large grains, they have good creep resistance at relatively high temperatures. So creep is one form of failure mechanism that we will learn in the next chapter. It happens at elevated temperatures. So that means if we need to choose a material that will serve at high temperature, we need to use materials or metals with large grains. And if we need to select material that will serve at low temperatures, then we need to choose metals having small grains. And there is an equation to describe the dependence of the average grain size D on the heat treating time. So D is for example, is the grain size we want to have. And D0 is the initial average grain diameter before the heat treatment. And those exponent is typically 2. We use 2 for most metals. And K is a material constant. It depends on the temperature where the heat treatment is carried out, but is independent of the time t. Let's see one design problem to see how to use the concept we just learned about cold working and also heat treatment to achieve the desired property for a given material. We have a cylindrical rod of brass originally 10 mm in diameter, which is to be cold worked by drawing to a final diameter of 7.5 mm. And the circular cross section will be remained during deformation. A cold worked tensile strength should be at least 380 megapascal and a ductility of at least 15% in elongation are desired. So explain how this may be accomplished. So first of all, we know for cold work, including drawing, it will increase the strength of the material, but will decrease the ductility. And also, the properties are affected by the percentage of cold work. If you still remember that equation, the percentage of cold work will affect the change the tensile strength and also the ductility of the material. So again, the more cold work we do on the material, the higher the tensile strength will be for the material, but the lower ductility for the material. Therefore, we need to see, based on the given initial and final diameter, we can get the percentage of cold work to see at that cold work amount, what is the tensile strength and what is the ductility. So we have a plot that you can use from the textbook showing the brass, the percentage of cold work plotted versus the tensile strength, and also the percentage of cold work versus the percentage of elongation. Okay, so we're going to use that to check the corresponding tensile strength and the corresponding percentage of elongation to see does it meet the requirement here. First, compute the percentage cold work. We know the initial diameter is 10 mm, and after cold work, the final diameter is required to be 7.5 mm. And percentage of cold work is defined by the original cross-sectional area divided minus or the change in the cross-sectional area over the original cross-sectional area and change to percentage value. And we can rearrange this equation and also cancel out those common factors. And it becomes 1 minus the final diameter over the initial diameter squared in times 100. So the percentage of cold work is 43.8%. If we reduce the diameter just once by one drawing from 10 to 7.5, this is the percentage of cold work. Next, we're going to use the two diagrams, the percentage cold work versus tensile strength and percentage cold work versus ductility or percentage of elongation. So for 43.8% of cold work, from this diagram we can read from the diagram the tensile strength after this amount of cold work will be 540 megapascal, which is greater than the required. So far so good, right? Is greater than the required tensile strength of the material, which is good. Now let's check the ductility. Again, with 43.8% of cold work, we read the percentage of elongation, which is only 6%, but the required ductility is 15% of elongation, which means because of the high strength after this amount of cold work, the ductility is greatly decreased. It doesn't meet the ductility requirement. So what other options are possible? Well, how about this? We don't reduce, or we need to decrease the amount of cold work, seems like, right? Because at this amount of cold work, the ductility is much lower than what we need. So how about we take the steps, which means the initial diameter is 10, the final one is 7.5. Instead of doing one step drawing, how about we find an intermediate diameter between greater than 7.5, okay, and do code drawing or drawing once. After this code work, stage 1, code work 1, or code working 1, we do heat treatment. We recover the mechanical properties of the material, mainly to restore the ductility of the material, and then we do the second stage, cold work or cold working stage 2. And the final property only depends on the percentage of cold work at stage 2. We just need to make sure the stage 2 cold work value will give us the desired resultant property. Then we will meet all of the criteria. Again, between those two cold works, we need to do annealing to restore all of the properties. Now, let's check for the required tensile strength, which is 380. How much cold work should we do at least? Because the tensile strength increases with amount of cold work. So to reach the minimum value, that means we need to do at least 12% of cold work to have the desired strength for the material. And now for the ductility, it needs to be at least 15%. Also, we check 15%. For 15% of ductility, we need to have 27% of cold work. And again, to have more ductility, we need to decrease the amount of the cold work because ductility decreases with cold work. Therefore, we have to make sure the amount of cold work is less than 27%. Okay, now we have the range that we need to perform for the cold work or second stage cold work, which must be between 12% and 27% to have the desired strength and ductility requirements. Therefore, the procedures we're going to take will be first cold work to an intermediate diameter and anneal to recover the ductility and the tensile strength. And then we perform cold work again. And then we also know that to meet the criteria, the second or the last deformation step should be between 12 and 27% of cold work, mainly for the number of ductility to be remained. And we can choose any value between those two values. So let's choose 20%. It's a whole number, which is easier for us to use, right, in the calculation. Okay, now again, remember our plan includes an intermediate diameter. The initial one is 10, and there is a D intermediate diameter, and the final diameter is 7.5. So we need to see, in order to determine the percentage of cold work during the second stage of cold work is 20%. So with this information, we can find the diameter, intermediate diameter here, and then we can check our final answers, or we can plan our procedure in more details. Okay, so let's calculate the diameter after the first coat work stage, or the intermediate diameter DI. And again, we're going to use the percentage coat work equation, and that's the simplified version. We just reduced the percentage of coat work equation from the use of cross-sectional areas to the diameters. D final over D initial squared in times 100%. Rearrange it. We know the D final is 7.5. We know the percentage of coat work should be 20. And from that equation, we can calculate the diameter after the first coat work stage, or the intermediate diameter, which is 8.39 millimeter. So that means the first drawing we're going to do is we're going to reduce the diameter from 10 to 8.39, and then we're going to do anneal. And after the anneal, we will reduce the diameter further to 7.5, and we already know in our design this percentage of coat work is 20% of coat work, and we will have the desired tensile strength and the ductility with only 20% of coat work. In summary, we're going to take 3 stages. Stage 1, coat work, which will reduce the diameter from 10 millimeter to 8.39 millimeter, and the percentage of coat work can be calculated using the final and the initial diameters, which is 29.6%. Stage 2, heat treatment or anneal, which allows recrystalization to restore the ductility. Stage 3 is coat work again. We will further reduce the diameter from 8.39 to 7.5 millimeter, which is the required final diameter. And the percentage of coat work is 20%. And using this coat work percentage, we check the corresponding tensile strength, which is 400 megapascal, and the percentage of elongation, which is 24. And both criteria are satisfied. So in this chapter, we learned that plastic deformation occurs by motion of dislocations. And dislocations move in the slip planes along slip directions. And those planes and directions are usually the most close packed planes and directions. Strength is increased by decreasing dislocation mobility, and the strengthening mechanics including the grain size reduction, solid solution strengthening, and string hardening, also called coat working. After coat working, we usually do heat treatment or annealing for the deformed metal specimens. So the 3 stages in heat treatment or annealing include recovery, recrystalization, and GrainGrowth. The consequences of heat treatment include a softer and weaker material, but more ductile.